81 is another finding from OpenZeppelin's audit of FutureSwap v2, where it was a medium severity finding related to configuration, in which the code was not using upgrade safe contracts in FS token inheritance. For context, the FS token contract was intended to be an upgradable contract used behind a proxy. However, the contracts ERC20 snapshot, ERC20 mintable, and ERC20 burnable inherited from FS token were not imported from the upgrade safe OpenZeppelin library, but instead from their regular not upgrade safe counterparts that used constructors instead of initialize functions. The recommendation was to use the upgrade safe libraries. This is related to OpenZeppelin's initializable in 192 and other proxy related aspects we discussed in Solidity 201 module. The aspect of importing upgradable contracts in proxy-based upgradable contracts of 97 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of configuration in 165 and initialization in 166 that we discussed in Security Pitfalls and Best Practices 201 module. '82 is another finding from OpenZeppelin's audit of FutureSwap v2, where it was a medium severity finding related to error handling, in which the output of the ECDSA recover function was unchecked. Recall that the ECDSA recover function from OpenZeppelin returns a zero address if the signature provided is invalid. This function was used twice in the FutureSwap code, once to recover an Oracle address from an Oracle signature, and again to recover the user's address from their signature. If the Oracle signature were invalid, the Oracle address would be set to zero address. And similarly, if the user signature were invalid, then the user message signer or the withdrawer would be set to a zero address. Either could result in unintended behavior. The recommendation was to consider reverting if the output of ECDSA recover is ever a zero address. This is related to OpenZeppelin's ECDSA library we discussed in 166 of Solidity 201 module, missing zero address validation in 49 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of cryptography issues in 174 and error reporting in 175 that we discussed in Security Pitfalls and Best Practices 201. '83 is a finding from OpenZeppelin's audit of Notional, where it was a medium severity finding related to configuration, in which adding new variables to multi-level inherited upgradable contracts would break the storage layout. The Notional protocol used the OpenZeppelin contracts to manage upgradability with the unstructured storage pattern. When using that upgradability approach and when working with multi-level inheritance, if a new variable were to be introduced in a parent contract, that could potentially override the beginning of the storage layout of the child contract, causing critical misbehavior in the system. The recommendation was to consider preventing such scenarios by defining a storage gap in each upgradable parent contract at the end of all the storage variable definitions for future variable additions. In such an implementation, the size of the gap would be intentionally decreased each time a new variable was introduced, thereby avoiding the overwriting of pre-existing storage values. This is related to the various OpenZeppelin proxy aspects we discussed in 185 to 192 of Solidity 201 module, state variables in proxy-based upgradable contracts in 99 of Security Pitfalls and Best Practices 101 module, and broader aspects of configuration issues in 165 that we discussed in Security Pitfalls and Best Practices 201 module. '84 is a finding from OpenZeppelin's audit of GB, where it was a medium severity finding related to data validation, in which unsafe division was performed in R-divide and W-divide functions. For context, the functions R-divide and W-divide accepted the divisor y as an input parameter without checking if the value of y was 0. So if that were to be the case, the call would revert due to division by 0 error. The recommendation was to consider adding a require statement in the functions to ensure that y is greater than 0, or consider using the div functions provided in OpenZeppelin's Safe Math libraries. This is related to OpenZeppelin Safe Math library we discussed in 175 of Solidity 201 module, and function parameters in 138, along with the broader aspects of data validation issues in 169 that we discussed in Security Pitfalls and Best Practices 201 module. 85 is another finding from OpenZeppelin's audit of 1inch, where it was a medium severity finding related to timing, in which safe approve was used incorrectly. The safe approve function of OpenZeppelin's Safe ERC20 library prevents changing an allowance between non-zero values to mitigate a possible front-running attack. Instead, the safe increase allowance and safe decrease allowance functions should be used. However, the UniERC20 library simply bypassed this restriction by first setting the allowance to 0. That reintroduced the front-running attack and undermined the value of using the safe approve function. The recommendation was to instead use safe increase allowance and safe decrease allowance functions. This is related to OpenZeppelin Safe ERC20 library we discussed in 149 of Solidity 201 module, transaction order dependence in 21, and ERC20 approved race condition in 22 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of timing issues in 177 that we discussed in Security Pitfalls and Best Practices 201. 86 is a finding from OpenZeppelin's audit of OpenGamma, where it was a high severity finding related to denial of service, in which Ether could get trapped in the protocol. If a user sent more than the necessary ETH for a batch of actions in a specific context of the protocol, the remaining ETH was not returned to the user and would get locked in the contract due to the lack of a withdraw ETH function. The recommendation was to consider either returning all the remaining ETH to the user or creating a function that allowed the user to collect the remaining ETH. This is related to locked Ether in 29 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of numerical issues in 170, accounting issues in 171, and denial of service issues in 176 that we discussed in Security Pitfalls and Best Practices 201 module. 87 is another finding from OpenZeppelin's audit of OpenGamma, where it was a medium severity finding, again related to denial of service, in which the use of Solidity's transfer primitive might render ETH impossible to withdraw. For context, when withdrawing ETH deposits, the payable proxy controller contract used Solidity's transfer function, which could fail with a withdrawer smart contract if it did not implement a payable fallback function, or the payable fallback function used more than 2300 gas units for some reason. The recommendation was to instead use send value function available in OpenZeppelin's address library, which can be used to transfer the Ether without being limited to 2300 gas units, and address any reentrancy risks from the use of this function by following the check effects interactions pattern and using OpenZeppelin's reentrancy card library. This is related to receive and fallback functions in 33 and 34, and transfer function in 47 of Solidity 101 module, OpenZeppelin's address library in 159 of Solidity 201 module, avoid transfer send as reentrancy mitigations in 15, and fallback versus receive in 27 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of denial of service issues in 176 that we discussed in Security Pitfalls and Best Practices 201. 88 is a finding from OpenZeppelin's audit of endowment, where it was a high severity finding related to timing, in which a reentrancy vulnerability was present because of not following the checks effects interactions pattern. For context, the finalized grant function of the fund contract was setting the grant complete storage variable after a token transfer, and could therefore be used to conduct a reentrancy attack leading to the contract funds being drained. The recommendation was to always follow the check effects interactions pattern where the contract state is modified before making any external call to other contracts and use reentrancy guards for such functions. This is related to OpenZeppelin's reentrancy guard library we discussed in 157 of Solidity 201 module, reentrancy vulnerabilities in 13 of Security Pitfalls and Best Practices 101 module, along with the broader aspects of timing issues in 177 that we discussed in Security Pitfalls and Best Practices 201 module. 89 is a finding from OpenZeppelin's audit of Audius, where it was a high severity finding related to auditing and logging, in which no events were emitted while updating the governance registry and guardian addresses. For context, in the governance contract, the registry address and the guardian address are highly sensitive accounts, which could be updated by calling set registry address and transfer guardianship respectively. However, these two functions did not emit any events, because of which stakers who monitor the Audius system would have to inspect all transactions to detect if any address they trusted was being replaced with an untrusted one, instead of simply subscribing to events emitted. The recommendation, therefore, was to consider emitting events when these addresses were updated to make it more transparent and easier for clients to subscribe to the events when they want to keep track of the status of the system. This is related to missing events in 45 of Security Pitfalls and Best Practices 101 module, along with broader aspects of auditing logging issues in 173 and principle of compromise recording in 201 that we discussed in Security Pitfalls and Best Practices 201 module. 90 is another finding from OpenZeppelin's audit of Audius, where it was a high severity finding related to identification, in which the quorum requirement could be bypassed with Sybil accounts. For context, while the final vote on a proposal was determined via a token-weighted vote, the quorum check in evaluate proposal outcome function could be bypassed by splitting one's tokens over multiple accounts and voting with each of those accounts. Each of those Sybil votes increased the proposal's num votes variable, which meant that anyone could make the quorum check pass. The recommendation was to consider measuring quorum size by the percentage of existing tokens that have voted, rather than the number of unique accounts that have voted. This is related to the broad aspects of token handling in 159, accounting in 171, and access control in 172 that we discussed in Security Pitfalls and Best Practices 201. 91 is another finding from OpenZeppelin's audit of Audius, where it was a medium severity finding related to timing from inconsistently checking initialization. For context, when a contract was initialized, its isInitialized state variable was set to true, and because interacting with uninitialized contracts would cause problems, the require isInitialized function was available to perform this check. However, this check was not used consistently. So for example, it was used in the get voting quorum function of the governance contract, but not used in the get registry address function of the same contract. This could be misleading and cause uninitialized contracts to be called. The recommendation was to consider calling require isInitialized consistently in all the functions of the contracts, and if there were a reason to not call it in some functions, consider documenting that, or alternatively, consider removing this check altogether and preparing a deployment script that would ensure that all contracts were initialized in the same transaction that they were being deployed. This is related to the broad aspects of initialization issues in 166 and also the timing and ordering issues in 177 and 178 that we discussed in the Security Pitfalls and Best Practices 201 module. 92 is another finding from OpenZeppelin's audit of Audius, where it was a medium severity finding related to data validation, in which the voting period and quorum could be set to 0. For context, when the governance contract was initialized, the values of voting period and voting quorum were checked to make sure that they were greater than 0. However, the corresponding setter functions, set voting period and set voting quorum, allow these variables to be reset to 0. Setting the voting period to 0 would allow spurious proposals that cannot be voted upon, and setting the quorum to 0 would allow proposals with 0 votes to be executed, which is very dangerous, as you can imagine. The recommendation was to consider adding validation to the setter functions. This is related to function parameter validation in 138, function invocation arguments in 146, along with the broader aspects of data validation in 169 that we discussed in Security Pitfalls and Best Practices 201 module. 93 is another finding from OpenZeppelin's audit of Audius, where it was a medium severity finding related to configuration in which some state variables were not set during initialization. For context, the Audius contracts could be upgraded using the unstructured storage proxy pattern, which requires the use of an initializer instead of the constructor to set the initial values of the state variables. In some of the contracts, the initializer was not initializing all the state variables. The recommendation, therefore, was to consider setting all the required variables in the initializer, and if there were a reason for leaving them uninitialized, consider documenting that and adding checks on the functions that use those variables to ensure that they were not called before initialization. This is related to the various OpenZeppelin proxy aspects we discussed in 185 to 192 of Solidity 201 module, initializing state variables in proxy-based upgradable contracts in 96 of Security Pitfalls and Best Practices 101 module, and broader aspects of configuration issues in 165 that we discussed in Security Pitfalls and Best Practices 201 module. 94 is a finding from OpenZeppelin's audit of Primitive, where it was a medium severity finding related to timing, in which expired and or paused options could still be traded. For context, option tokens could still be freely transferred when the option contract was either paused or expired or both. That would allow malicious option holders to sell paused or expired options that could not be exercised in the open market to exchanges and users who did not take the necessary precautions before buying an option minted by the Primitive protocol. The recommendation was to consider implementing the necessary logic in the option contract to prevent such transfers of tokens during pause or after expiration, or alternatively, if the described behavior was indeed intended, to consider clearly documenting it to raise awareness among the option sellers and buyers. This is generally related to OpenZeppelin's possible in 156 of Solidity 201 and broad aspects of timing and ordering issues in 177, 178, system documentation and clarity issues in 137 and 188, and business logic issues in 191 that we discussed in Security Pitfalls and Best Practices 201 module. Number 95 is a finding from OpenZeppelin's audit of ACO protocol, where it was a medium severity finding related to data validation, in which ERC20 transfers could misbehave. For context, the transfer from ERC20 function was used throughout the ACO token contract to handle transferring funds into the contract from a user. It was called within mint, mint2, and validate and burn functions, where in each case the destination was the ACO token contract. Such transfers may behave unexpectedly if the external ERC20 token contract charged fees. As an example, the popular USDT token does not presently charge any fees upon transfer, but it has the functionality to do so. In that case, the amount received would be less than the amount sent. Such deflationary tokens have the potential to lead to protocol insolvency when they are used to mint new ACO tokens. In the case of transfer ERC20, similar issues could occur and cause users to receive less than expected when the collateral was transferred or when exercise assets were transferred. The recommendation was to consider vetting each token used within an ACO options pair, ensuring that failing transfer from and transfer calls would cause reverts within ACO token contract. And additionally, consider implementing some sort of sanity check which enforced that the balance of the ACO token contract increases by the desired amount when calling transfer from ERC20. This is related to token deflation via fees in 107, guarded launch via asset types in 129, and broader aspects of token handling in 159 and data validation issues in 169 that we discussed in Security Pitfalls and Best Practices 201 module. 96 is a finding from OpenZeppelin's audit of Compound Protocol, where it was a medium severity finding related to auditing and logging, in which there was incorrect event emission. For context, the Uniswap window update event of the Uniswap anchored view contract was being emitted in the poke window values function using incorrect values because it was being emitted before the relevant state changes were applied to the old observation and new observation variables, and therefore causing the data logged by the event to be outdated. The recommendation was to consider emitting the Uniswap window update event after changes were applied so that all log data is up to date. This is related to broader aspects of auditing logging issues in 173, ordering in 178, and freshness in 185 that we discussed in Security Pitfalls and Best Practices 201 module. 97 is a finding from OpenZeppelin's audit of MCDEX MI protocol, where it was a critical severity finding related to access control in which anyone could liquidate on behalf of another account. For context, the perpetual contract had a public liquidate from function that bypassed the checks in the liquidate function, which meant that it could be called to liquidate a position, and with any user being able to set an arbitrary from address would cause a third party to confiscate an under-collateralized trader's position. So effectively, this meant that any trader could unilaterally rearrange another account's position and also liquidate on behalf of the perpetual proxy, which could break some of the automated market maker invariants. The recommendation was to consider restricting liquidate from to internal visibility from public visibility. This is related to aspects of function visibility specifiers in number 23 of Solidity 101, incorrect access control in number 4 of Security Pitfalls and Best Practices 101 module, and aspects of function visibility in 140, along with broader aspects of access control in 148, 149, and 172, and trust issues in 181 that we discussed in Security Pitfalls and Best Practices 201 module. 98 is another finding from OpenZeppelin's audit of MCDEX MI protocol, where it was a critical severity finding related to denial of service, in which orders could not be cancelled because when a user or broker called cancel order, the cancel mapping was updated, but that had no subsequent effects because validate order param did not check if the order had been cancelled. The recommendation was to consider adding that check to order validation to ensure that cancelled orders would not be filled. This is related to broader aspects of data validation in 169 and denial of service issues in 176 that we discussed in Security Pitfalls and Best Practices 201 module. 99 is another finding from OpenZeppelin's audit of MCDEX MI protocol, where it was a medium severity finding related to re-entrancy. For context, there were several examples of interactions preceding effects in the context of the checks effects interactions pattern or CEI pattern that we have discussed. The first example was in the deposit function of the collateral contract. The collateral was retrieved before the user balance was updated and an event was emitted. 2. In the withdraw function of the collateral contract, collateral was sent before the event was emitted. And 3. The same pattern occurred in deposit to insurance fund, deposit ether to insurance fund, and withdraw from insurance fund functions of the perpetual contract. These reentrancy opportunities would affect the order and contents of emitted events, which could confuse external clients about the state of the system. The recommendation, therefore, was to consider always following the check effects interactions pattern or use reentrancy guard contract to protect those functions. This is related to OpenZeppelin's reentrancy guard library we discussed in 157 of Solidity 201 module, reentrancy vulnerabilities in number 13 of Security Pitfalls and Best Practices 101 module, along with broader aspects of auditing logging in 173 and timing issues in 177 that we discussed in Security Pitfalls and Best Practices 201 module. 100 is another finding from OpenZeppelin's audit of MCDEX My protocol, where it was a medium severity finding related to timing, in which governance parameter changes were enforced instantly. For context, many sensitive changes could be made via the function set governance parameter, such as the initial and maintenance margin rates or the lot size parameters. And these new parameters would instantly take effect in the protocol with important effects on protocol users, some of which could be perceived as being as negative impacts. The recommendation was to consider implementing a time lock mechanism for such changes to take place, because by enforcing a delay between the signal of intent and the actual change, users would have time to decide to continue engagement with the protocol or exit their positions as necessary. This is related to OpenZeppelin's time lock controller library we discussed in 182 of Solidity 201 module, and time delay change of critical parameters in 163, along with broader aspects of timing in 177 and trust issues in 181 that we discussed in Security Pitfalls and Best Practices 201 module. 101 is another finding from OpenZeppelin's audit of UMA protocol, where it was a high severity finding related to data validation in which votes could be duplicated. For context, the data verification mechanism used a commit reveals key to hide votes during the voting period, where the intention was to prevent voters from simply voting with the majority. However, the design allowed voters to blindly copy each other's submissions because votes were not cryptographically tied to the voter, and so really undermined the objective of the commit reveals key. The recommendation was to consider including the voter address within the commitment to prevent votes from being duplicated, and also consider including the relevant timestamp, price identifier, and round ID as well to limit the applicability and reusability of a commitment. This is related to broad aspects of data validation in 169, accounting in 171, cryptography in 174, and business logic issues in 191 that we discussed in Security Pitfalls and Best Practices 201 module. So with that, we have come to the end of the 7th module on Audit Findings 101, where we reviewed highlights of 101 findings of critical, high, medium severity levels from public audit reports of Consensus Diligence, Trail of Bits, Sigma Prime, and OpenZeppelin. We recognized their severity, category, key highlights of the vulnerability, and the proposed recommendations. We then also connected them to concepts from Solidity and security pitfalls and best practices of earlier modules. So hopefully we now have a much better idea of how such security pitfalls and best practices would have translated into vulnerabilities in real-world protocols had it not been for security audits detecting and reporting them. I would strongly recommend reading the audit reports referenced for these findings here to get a deeper understanding of the protocol logic context and details behind the reported findings, where we have only touched upon some key highlights here in the interest of breadth of coverage and time constraints for time. In the next module, we will review 100 more findings.